Okay, let's get going. It's almost 6 after. So I had two goals for this meeting. One is to finish up the Deep Lab V3 plus discussions and complete that paper, and then hand it over to Steve to kind of take us through. Is it Catalyst, Steve? I forget the name of the
It is Catalyst, yep.
yeah, to take us through your Catalyst explorations and code, since that was of interest to many people. That's another platform that we could use besides FastAI to kind of incorporate several of the models that are available and so on. So those would be the two objectives. You'd be ready to go through that, Steve, once we're done with the Deep Lab V3 Plus discussion?
Yeah, I'm not sure how much there is to it really. Like I'll go through what I've done, but I know that like Mehul had said a couple of weeks ago, like he'd been trying like Vast AI. I'm not sure if he wanted to cover that as well. If he,
Yeah, if you're done with what you have, then maybe Mehul can share that as well. And the other thing which would be of definite interest to everyone, and maybe we can make time again next week to go through that as well. If since we may run out of time this week, is use of TPUs. And have you had a chance to check out TPUs with usage with Catalyst? You were trying to play with that.
I played with it. I haven't got it working.
Okay.
Yeah, so it seems to have been just like sort of added into Catalyst, and like it just came out in. It was only the new release came out last week, I think.
Okay.
Prior to that was a sort of technology preview that they'd issued, and it had a few bugs in it. So their documentation is very sparse, and it looks to me they're like already been like a paper out or like a Medium article out about how to put TPU support into PyTorch. So it doesn't look much different to that, but yeah, I've tried to put it in, but so far I was getting like sort of errors that the things weren't on the TPU for, I don't know, the loss functions and stuff like that. So unfortunately, I haven't managed to get it working yet.
Okay, so in which case we'll wait maybe a couple of weeks and get through the discussion. Hopefully that, and I think Mehul was saying he had some luck with using TPUs on Kaggle, so we can kind of combine the two things side by side so we can get an idea, and maybe 2 weeks out might give enough time if it works. If not, we'll wait further. But as and when you get the chance and you see working, drop a line in the Slack channel, and then I'll definitely make time to schedule, because that would be of, I think, significant interest, given that Colab provides access to TPUs too, I think, and if we can use that, then and figure out a way, a lot of the computations can get much faster.
Yeah, I can create a notebook with TPUs on Kaggle, but sorry, on Colab, but I just can't run them yet.
So Mehul, would you be able to share what you have in a week or so?
Yeah, I can. Yeah, I can share in a week or so. I've been mostly. All the luck I had with the TPU has only been with TensorFlow.
Okay, that's fine too. I mean, if you can still share what's possible,
Sure.
and Steve can get Catalyst working in a week or two, then it may be a good, kind of spend an entire session on just TPU usage in Kaggle with TensorFlow and with Catalyst. If Steve can, either has luck, whenever either of you are ready to go, just drop a note and I'll schedule it so that we make the time for it. I think it's worthwhile, given compute is kind of a bottleneck for any Kaggle competition. It takes 8 hours minimum, sometimes longer than that, blah, blah, blah. So, if we can accelerate that, then we can accelerate learning through single models. I mean, we can always go for ensembles, but that's kind of the last resort.
Srinivas, and Steve, do you have a feeling for whether the TPU would be faster than the Colab Pro account that you guys use?
I have some notes on that. So the Colab Pro also, so Colab Pro gives you both GPU and TPU, and it gives you, it says it gives you a, so TPU, like the problem with the TPU has been, so there are 3 versions, version 1, 2, and 3. Okay, and it's, as from what I understand, like, so version 3 has 128 MB of RAM. So if your batch size on the GPU was 2 or 3, now suddenly you can go to 16 or batch size 24, just because there's so much RAM. And I know, so the Google Colab Pro has, it says, when you get the Pro version, you get a better TPU, but it doesn't give you all the details. Like, okay, what is it? Well, I can't find anywhere that, which version of TPU is available. And so far, it seems like the Kaggle TPU is the best, is the best version. But just because, like I had a friend who ran some experiments, and he found like the Kaggle TPU is the fastest. But the Kaggle TPU has a 3-hour limit. So you get 30 hours, but at a time you're only allowed to use 3 hours.
30 hours a month?
30 hours a week.
A week. Okay. Wow, that's great.
Yeah.
And so the Kaggle one is from your experience or from your friend's experience is better, but the question is I know Kaggle has some, like you said, there's some Medium articles out about how to use Kaggle's TPUs. Does Google Colab also provide some kind of tutorial to help you to get started with its TPUs?
Does Google Colab what?
Does Google Colab Pro give you some kind of a tutorial to help you get started with its TPUs?
Yeah. I can share that link.
Okay.
Yeah, they have a couple of links. Yep.
But by the way, Joseph, the 30 hours you find out when you're doing, for example, the segmentation problem, Sevastral and stuff becomes a bottleneck very quickly when your single model takes about 8 to 9 hours to train and infer.
Wow, okay.
So you run 3 cycles of 3 different things and you're done for the week. You can't do anything more.
Jeez, okay. So now I see why you guys went to Pro.
Pro's good as well.
Yeah.
Oh, that's even with
GPU
Pro you have
point of view. Yeah, like I was just using like normal Colab to start with, and like every time you logged on, I would end up like with a rubbish GPU that would go slowly. And as soon as I've gone to Pro, yeah, like it seems to be sort of top of the range GPUs, so like they run sort of 5-6 times faster maybe, and it's been much better. So
yeah,
but they still limit you to.
No, Colab Pro doesn't have a limit. Colab Pro is you can just run as long as you pay the $10 a month. Okay. You can run as much as you want.
Yeah. There is like a time limit.
Right.
I can't remember what the time limit is. It's something like 12 hours or something. But yeah, I've never sort of hit that yet.
12 hours at a time, then you mean?
Right. 24 hours at a time is max you can run.
I see.
Is it? Yeah. But yeah, I haven't got models that go that long yet.
Isn't the time limit just for free users? The Colab Pros, you don't have the time limit cap, right?
Colab Pro clips you off at 12 hours. You can't run a notebook longer than 12 hours. I'm sorry, 24 hours.
Okay, so it doesn't change so much from the Colab free version, right?
It's better than the free version because you get higher end GPUs and the
24 hours, as Steve said, at least for now, we don't hit that limit in practice. Because a single running for 24 hours, haven't yet encountered that problem. Single run needing to run 8-9 hours easily.
Okay.
So, and as Raquel, multiple people mentioned, Colab Pro gives you both much faster as in GPUs, and once you can learn, and that's why I was saying that it would be good if we can figure out some smart ways to use TPUs that Mehul and Steve can share as we move forward in a couple of weeks, then it would be even faster. But obviously, given TPUs are even more expensive, they do limit the hours there. But I don't think Colab Pro is going to limit you in practice from running anything. There is a limit, as Raquel points out, of 24 hours, but so far I haven't seen people encountering it too often or complaining about it.
Yeah, on Kaggle Pro, sorry, that's not Kaggle Pro. Sorry. On Kaggle, there's so many versions of on Kaggle, like in the there's that melanoma competition, which has 10,000 images or something for training. And people are reporting that basically everybody's given up on the GPU. They're just, because the GPU takes like, say, 10 hours or 12 hours to run your experiment, like a 5-fold experiment. And the TPU is running it in 3 hours.
Yeah, so there we go. The TPU is, I mean, obviously given the architecture, hardware and stuff, it's just expected to be so much faster, but the frameworks need to start supporting it. TensorFlow, obviously, given everything is Google. Colab Pro and Kaggle are both Google. So it's kind of, you know, they're just selectively releasing. I mean, those guys are just segmenting the market because they can release to the same TPUs on Kaggle that they do on Colab Pro or vice versa. But anyway, it's kind of up to them as how much they charge and what they want to do with the free versus charge, blah, blah, blah. But I do expect Colab Pro to quickly get TPU because you pay for it, whereas even Kaggle is free. Anyway, so yeah, whenever you guys are ready, even one or the other, just let me know and we can schedule it in. So without further ado, let's jump into DeepLab v3 Plus. And given what Steve said, maybe even if it takes most of our time, we can do that. And then I lead to Steve so he can share what you've been able to do with Catalyst. And then in the next meeting, hopefully we'll have a chance at looking at implementation either of PSPNet or of DeepLab v3 Plus.
I got those running, so
cool.
we have time.
So that'll be, so next week, if we have time this week, but let's give Steve his due this week and then get to the PSPNet implementation next week. Start off with that, that'll be great. And then jump into either DeepLab v3 implementation or HRNet discussion. Okay, so I'll start sharing my screen on DeepLab v3 Plus. Okay, can you folks see the paper now?
Yep.
Okay, so I think we had kind of gone through some of it. So the early part, I'll kind of move through it fairly quickly, and then we'll dive into some of the specific details and then the results. If you recall, and I think Steve made the point that earlier or in our previous discussions that DeepLab v3 Plus compared to v3, I think the two key things that they add with respect to v3 are, one, the fact that they use the exception network as the backbone, which means, and the reason they do that is they want to use this depth-wise separable convolution, and we'll get to that in a minute. And the second is the fact that they use encoder-decoder. The remaining concepts are carryovers from what we have already seen. That is the parallel Atros convolution and the pooling that they apply to the Atros convolutions and the full image that they take in as well. That is the image level convolution. So those are carryovers from the v3 paper. The plus aspect comes in from the encoder decoder and the depth-wise separable convolution. Those are the two new ideas that they bring in. So they point out, how much you need to do in order to, how much computation in order to do when you want to keep the denser output features. And therefore, well, not therefore, separately they add the decoder module to recover the specifics of the object boundaries and using Atros convolutions at different rates. And the Atros convolution helps you kind of keep the budget on computation reasonably small. And then there is this depth-wise separable convolution. Have people kind of looked at depth-wise separable convolution, or should we, I think they look at it in a little more detail, I think, coming up. So let's defer that. And then they combine Atros convolution, but they combine the Atros concept with the separable concept. And the atros we have already seen is just the dilated, or the the fact that you use wider receptive fields, and they also use different rates, meaning you go over larger portions of the image, thereby enhancing your receptive field. But then they also do this separable part, and we'll get to that. So they talk about
the depth-wise separable convolution is a very simple concept. It's it's better when you get the image, but we can
they have it coming up in discussion with images in a minute. This is a picture which I think is good in understanding what they are doing in this paper, and in fact in the prior paper, which unfortunately they didn't have the equivalent of this image in the prior paper, which would have explained or simplified the explanation of many things. In the encoder, which is the same as what they do for the DeepLab v3 paper, they do the multiple atros rates. That's the 3x3 convolution at rate 6, rate 12, and rate 18. And then they do a 1x1 convolve on the image, as well as the full image pooling. And then they concatenate all of those.
Have you searched on this image pooling technique? I still don't get what is it doing here? What is this image pooling?
I think Rekel kind of explained it last time as well. So I'll let him explain it. He gave the best explanation for it of what you're trying to do.
Cool, yeah. I think the main idea there is you're trying to look at your original image at different resolutions. And the way you cover different resolutions is you either do bigger convolutions. So you move from like a 1x1 to a 3x3 to a 5x5 to a 7x7. So your field of view keeps increasing like that. The problem when you do more than, let's say 3x3, when you start going to 5x5, 7x7, your number of computes start increasing. So their strategy is, instead of doing something like that, let's keep the number of operations same, but increase the field of view. And that's what the concept of the dilated convolution is. So in essence, you're basically just putting in zeros between two filter values. If rate R is equal to 6, you're basically sampling at.
No, I'm good with the concept of a true convolution, and which is the same as the dilated convolution. But the specific image pooling technique is what intrigues me, because it's a different technique they use.
You could do the exact same thing probably with, instead of doing 3x3 at rate 12 and 3x3 at rate 18, you could replace those with like 5x5 and 7x7. You're seeing bigger field of views, right? So instead of just seeing like a 3x3 portion, you're seeing a lot more of the context. Your surrounding pixels, you're incorporating more into your thing.
The problem with doing his question is specifically just the last block at the bottom, which is image pooling, which we saw.
Yeah, it's because they don't talk anything about this technique on the DeepLab paper. I think it's a technique they use on a previous paper.
Right. Yes, they do talk about it here. Can you still see my screen?
Yes.
Yes.
Okay.
Yes.
So so here they talk about this image pyramid, and so as this is the particular part that is being reused in the other paper. That is, they use the full image and use some level of convolution, say 3x3, still to get the final result here that is shown, and they merge that with all these others of the same h by w size. So that's what the image pyramid aspect, or the specifically refers to in the previous paper. So let me show you. See, even here, the B image pooling is independent of these, but is concatenated and calculated in parallel with the others. And that's the image pooling that they're referring to. And when we discussed this last time, I think, Rekil, you had mentioned that that is just directly applying the 3x3 convol, but on the whole image, original image. Is that right?
Are we talking of pooling?
Just this image pooling, this particular, you see this thing
Yeah, that's
here?
just average pooling. So you basically get down to like something like a 1x1 from your feature map.
And
not
this,
the original image, feature map.
So this image pooling
Yes.
is again the same thing, right?
Yes, yes.
You just essentially.
Oh, that is what your question was. Oh, sorry.
Yes, that was his question.
So the image pooling is basically giving you the context of the whole image. That's what image pooling is doing.
So you take, instead of doing all these rates, all these convols, you just do a pooling on the full-sized image and you generate this, whatever this color is.
Right, this full-sized feature map, not the full-sized original image though.
Yeah, what I meant is you pool on the full-sized original image and you get this feature map. Is that right?
No, sorry, hang on. You said pool on the full-sized original image?
Yes, because of this diagram. Let me show you why I said what I said. Because of this diagram.
So that's what. So I don't think image pyramid is used in that at all. Image pyramid would be meaning you have to go through different resolutions, right? The image pooling is just talking about going with that feature map, which is like H/16, W/16 to something like a 1x1. So that is basically, so you've done this operation of 3x3 at different rates. You've done this 1x1. So they're all seeing at different views, right? And the 1x1 is adding the whole context of the image. That's the way I understood that.
Okay, so just to clarify, it's, you know, and because it's confusing since they mix up, I think, two similar sounding concepts. So what I hear you say and what I take away from it is image pyramid would refer to multiple feature scales and merge them.
Yep.
Right? And that's the feature scaling variation independent of the heteros convolution variation and using different feature scales and pooling them. Whereas the image pooling here is referring only to taking whatever the convolutions are applied on, meaning whatever feature map here or image that you are applying a pooling, but at the full image level. When I say full image, I don't mean the full original image, which is here, but at this level, and then just pooling it appropriately to generate this particular pink.
Well, I looked up here and I found that this concept was introduced on the ParseNet paper. It's a 2016 paper.
Yeah, they say width, or I forget, wider is better or something like that.
Yeah, that's the paper, but I didn't read it. They have a nice picture there, but I couldn't understand by the picture. If you could open up in a new tab real quick, just for everyone to see the picture. It's ParseNet paper. It's on the second page. It's one of the first pictures. Yeah, that's the first picture, the first figure. The image pooling is the letter E here. But I couldn't understand this by looking at the picture. I didn't have time to read the whole paper, but it seems that they are trying to extract the global context with a global pooling of the feature map, the image, and then they do a normal convolution. I don't know, this L2 normal operation, and then they concatenate it.
Yes, and in fact, that's why I was saying if you retain kind of the idea of applying pooling at the full size, when I say full, at on the feature map, then that's what you get into here, because all you have done is instead of applying any convolution, you just directly pool on the feature map that you are working on, and that generates one of the feature maps that you concatenate.
Okay, you do a global pooling through all the channels
Exactly.
to
You
get
just do the global pooling
concepts.
of whatever feature map that you're processing at this state that you're running these convolutions on, and generate this, which gives you the full feature map context that you can then concatenate with the heteros convolutions at different layers and the 1x1 convolution, which is essentially a full layer convolution.
I think they get the picture. With that picture, my do the what they are doing there is that they are doing this global pooling, and then they do a non-pooling technique that I don't know, maybe it's replicating the
Basically something like
pooling
upsampling.
layers. Yeah, it's not maybe it's a kind of upsampling, but it's a global pooling will get, it will be a pooling over all the channels to output and ending a single channel with the max
No, your number of
values for
channels
each
still
channel,
remain
right?
the same, right? The number of channels won't change.
No, the global pooling will change the number of
It
channels.
will only change height by width.
Yeah, it won't change because pool, you just pool in the HW dimension, not in the width or the channel dimension.
That's why if you go back to the parsnet paper, you can still see that the Z dimension still exists.
Oh, you close the screen sharing settings.
Yeah, we lost it.
Okay, moved.
So, there it is.
Here they have a global feature that is like a single channel with information, with global information from your entire feature map.
No, those are multiple channels, all of the size 1 by 1. So it's 1 by 1 by number of channels.
Oh, okay. So it's multiple channels, but you get a single value for each channel, a single max value for each channel.
So that's what gives you the global context for each channel.
Oh, now it's clear for me. Okay, so
each of these features is like, you look at the global aspect of it, and then that's what is propagated.
So the key being that in this case, you get, instead of, I mean, you're trying to get it by different rates, but you ensure that you have the full images context by doing the image pooling, which is pooling at the full image of H by W at this rate, and then concatenating, including that as a concatenation.
Yeah, so I have a question about what comes in. So I see this, the image comes into this DCNN, which I assume is a fully connected neural network. No, sorry, it's a DCNN, a dynamic, whatever does this D stand for? Deep CNN. Okay. Now, and then it says truth convolutions. Now that's confusing because, okay. Inside that purple box is all the stuff in the brackets. Is that correct?
Yes, for a particular layer, and they do it multiple times.
Okay.
So this is, you can think of this as a conceptual image. This is repeated multiple times, and we'll look at that in more detail as we go through. But this is the concept of what happens in a particular heteros convolution layer. And there are multiple of these that happen, I think, as we go through but this is what is happening within this heteros convolution, which composes the deep CNN layer.
Got it. So what's inside that purple layer labeled truth convolution is all the stuff between the brackets.
Yes.
Okay, so now my question is, how does the image, so what is the input for the image pooling? Is that just the image itself, and then there's some kind of a fully connected neural network that maps it to the right size, or?
And we'll see that, but that's why I kept referring to this particular purple box, which has the heteros convolution title, as an image at that level. Or, like, I think if I recall correctly, and we'll quickly figure out whether I'm right or wrong, but I think what they do is they have a stem which brings this down by, and Rekiles, I think, looked at it by 1/4, if I'm not mistaken.
No,
Okay.
16, right? Output slide was 16 or 8.
Yeah, it was by some fraction. I forget what exactly the fraction is. You think it's 1/16, Rekil?
Yep, 1/16 or 1 by 8.
Yeah, so either of those, and then you begin this process where you apply that within the Atos convolution, which you are, once you do these things within the Atos convolution block, you also then stack the outputs and then do a 1-by-1 convolve.
Right.
Okay, but you in encoder, much like if you're familiar with UNet, you continue down this path with multiple repetitions of this guy, except that you then at a particular point, and which is where what we'll see in more detail as we go through the paper, you do the 1-by-1 convolve at two particular, in this case, one particular point in the network, generate this green feature map, you upsample that feature map and provide it to the decoder. Now, the decoder takes its input, one of its input from the output of this Atos convolution block before I think all these things are done to it. Just apply the 1-by-1 convolve and generates this purple looking feature map, which gets concatenated with the output of this encoder and a 1-by-1 convolve applied to it, upsampled by 4, then you will find out that these two sizes are the same, which is why it allows you to then concat those two to form this particular sandwich of green and purple, to which you apply a 3-by-3 convolve, upsample by 4, predict on it.
Okay, so one question is that a truth convolution, if it is what we think it is, which is basically the stuff inside the brackets, then the output of that layer is this concatenated series of colored erasers or whatever stacked on top of each other. Right, but that is but then the output going downward should be exactly the same thing going into the 1-by-1 convolution, and so that pink thing to the left of the bottom, so the right of the bottom 1-by-1 convolution should be the same size as the green thing to the bottom of the 1-by-1 convolution on top. I don't see why they're different sizes.
Because here you have done a 1-by-1 convolve and then again a 1-by-1 convolve.
Oh, that's a good question. I have the same doubt as Joseph.
And we can look at, that's where you'll have to kind of dig into the code and the further details of the picture. But the takeaway would be that this is just what I would say. First of all, in the picture itself, it's clear that here you're going through, this bluish thing is just one of the sandwich stack or the eraser stack.
Well, I think we should go back to the figure 1. That maybe the figure 1 will clear our doubts a little bit better, because on the letter C of figure 1, we can see that at the end of the encoder, the final image is downsampled by 8 times. So it do 2 upsamples of 4 times on the decoder part. So maybe the ending here will be like the thing that is going to be upsampled 4 times, and then the part that goes directly to the 1-by-1 convolution and then it's concatenated is the thing at the middle here.
Yeah, there are 2. There's one, this is the thing that comes in, and then there's a 4-by, and like you pointed out correctly, this is 16x upsample going this way. So this obviously 16x downsample going that way.
So what we thought that there was that this little square called a true convolution is not the things inside the brackets. The brackets are the parallel true convolutions, the spatial pyramid pooling, what is called here. And the thing that inside the square called true convolutions are the cascade true convolutions.
Yeah, so that's what I was saying even earlier, that this is only this is not all of it. There are multiple levels. This is the entire encoder. So it has multitude of this repeated. So it's not just one, it has these going through it. And it's, what is blown up, as you said, is that part.
I think it's just once, right, Srinivas? I don't think it's a multitude. I think.
Yeah, what I meant to say, yes, you're correct, Rakel. So what Rakel is clarifying, I think, is that this particular atros thing is applied. This blow up happens corresponding only to that guy.
Yes.
But what I was saying is the encoder does go through all of that.
Correct.
Layers.
Yes.
So when he shows the whole thing, that's why I call it like more like a schematic diagram rather than an accurate description, is this encoder block is supposed to encompass all of this
left-hand side,
the left-hand side. And
but as Antonio said, the downward output of that block is the middle piece. So it's not scaled the same as so it's 4 times bigger, which makes sense, right? The rightward block that goes from 0.5x to it's the purple layer in the middle there. That output, that arrow to the right, is the same as the downward arrow.
Yes.
I think that's what Antonio said, and I think that sounds
correct. Right. That's correct. Yes, this downward arrow is the middle guy.
Not that one, I think, Srinivas, the one on the left, right?
The one on the left, yeah.
Oh, sorry, here, yes.
No. In
the other picture.
Oh, I'm pointing to, yes, in the...
block C, in part C, the middle arrow, the middle rightward arrow, in that C, yes, that corresponds to the downward arrow from the atruce block in the picture below.
Yes, in fact, that's kind of what I was saying. Rakel, are you saying that's not right?
No, that is the one, yeah.
Okay, that's what I was pointing to.
That one, yeah.
This guy is that guy.
No, that's
the guy on the left-hand side.
Sorry, this guy is the top guy, correct?
Yeah.
Correct.
Yeah.
Because there is 2 upsamples. In fact, the way I correlated it, there are 2 upsamples. The first upsample is coming in from the top. And then this upsample by 4 happens here. So this guy, which is upsampled by 4. So in a sense, to coordinate the second diagram with the first or with this one, you have to, the way I do it is to say there is an upsample from here to the prediction by 4x. So this layer, if you will, in this diagram corresponds to the output here, because then you upsample and you get to the prediction. Okay. And the way I orient myself, at least, and tell me if I'm right or wrong, and the way you do the upsample by 4 to concat. So this guy coming in here, then you upsample by 4 and concat. You go back to this diagram, you upsample by 4 and you concat.
Yep.
So I orient myself by where the upsampling and then this and this guy get concatenated. So this arrow coming in from here, right, where you upsample, this upsampling by 4x is corresponding to this upsampling by 4x. Okay, after which you concat what's coming in and this guy. So these 2 arrows correspond respectively to this arrow and this arrow, one coming in from the atros part, which is the encoder part, and the other directly feeding in from what is your input path. So they haven't shown the details here, but these 2 arrows correspond to this guy and this guy. So one of the input going into the upsample by 4 is that output of stacked eraser stack, but you have to apply a 1x1 convolve and then upsample by 4. So which is what they have not shown in this diagram. So you take this eraser stack, do a 1x1 convolve, and then upsample by 4. And then you take this input path and you do again a 1x1 convolve, and then you concat. And the 1x1 convolve in both directions, in my assessment, and we have to look at the code, is to ensure that the channel depths are the same on both, and then you concat. But you know, typically you do the 1x1 convolve to ensure that the channel depths are varied, which I'm assuming is the case. So then you do that part. You've concatenated this 1x1 convolve from the encoder and the eraser stack, apply a 1x1 convolve, and then a 4x subsample, and then you concatenate to get a 2-layer stack. And then here you do a 3x3 convolve, which is this guy, and then again you upsample by 4 to make the prediction. Is that right? Everybody aligned?
Yeah.
Yeah, I
This
think
figure and the
that's it.
previous paper's figure, they show slightly different things. The previous DeepLab V3 shows you what the convolution maps are. And this diagram kind of shows you with those colored stacks, the outputs of the convolution maps. So that's why here you see that all the things that you're stacking together, they have the same size. But in the V3 paper, you'll see the actual convolution masks that are being applied. So just to keep that in mind when you compare this with that.
And
So that's
one more. Yeah, that's the main idea. But also, I have this other doubt that the depth-wise separable convolution. After we discuss what it actually is, I would like to know if they are using this all these columns here are depth-wise convolution, or this whole schematic means that they are doing the depth-wise separable convolution.
Yeah,
let's
we'll get to that in a minute. The answer, I believe, is that yes, all these 8 rows convolutions are depth-wise separable convolution. So they combine the concept, and when they say here 8 rows convolution, they're actually referring to 8 rows separable convolution.
Yeah,
what they
that's
use as
what
a
I
term.
thought.
That's why you're using an exception, right? You're not using a resonate at the head.
Correct.
Because exception has
backbone.
the depth of it.
Yeah. So with that lead in, diving into the depth-wise separable, it's just basically, I think Rekal mentioned this, and I'll have to switch to this. Are people familiar with the depth-wise, or should we spend a minute or two discussing that? Let's do it for now. The only thing is I'll have to switch for a minute because I have to stop sharing. Go to this. Give me a minute while I.
If you're still on Chrome, it's just sharing the application. So I think you should be good. You don't need
No, the problem is this medium post
PDF?
problem that I talked to you
I
about,
see.
right?
Okay.
So I have this useless thing of it makes me.
The incognito stuff. Okay.
Yeah, exactly. So let's see which one am I sharing. It doesn't seem like I'm sharing the right one. Give me a minute while I figure this out. Let's see. Maybe it may not be the correct one. Are you seeing the
Yep,
volcanic
that's the one. Yeah.
thing? Okay, good. So let's look at the example of depth-wise convolution. And in fact, for those of us who were in Joseph's, the discussion on CS224N, we were just looking at convolution even on words. And the key point he was emphasizing is, convolution is done across all the channels, right? So that's a key thing to remember. In this case, we begin to violate that particular assumption, and we don't do it across all the channels, but we do it per channel. So that's the big difference of depth-wise. This is the separable convolution, and the depth-wise separable is right here. So, and apparently, MobileNet and exception, as you can see, use that, and exception was the paper that introduced it, and it, as we'll see toward the end very quickly, it reduces the number of computations you have to do. So, so the 2D, 1D, interest of time, I'm not going through the details. You can look at, there's a very good reference, like we provided this, I mentioned before. The point is that, you go through the entire depth to create the output using a single filter. So the filter of 5 by 5 is applied across the entire width dimensions of the image, for example, that you're applying.
3 by 3, yeah.
Yeah, the 3 by 3 in this case, correct. Apply it to the entire depth. And then in this case, he's saying a 3 by 3 applied there, and then begin to discuss the depth-wise separable. So in this case, you split it a 3 by 3 per channel. So you can see now that the 3 by 3 of this first 3 by 3 filter is applied just to the first of the 3 channels. The second channel of the image gets this 3 by 3 red filter, and the third channel of the original image gets the 3 by 3 green filter.
So in the original block where you had this 3 by 3 by 3 in orange, that means you had copied each matrix on top of, so each 3 by 3 was a copy of the other one. So there were 3 copies of a single 3 by 3.
Yes, it's as much as the depth of the channels, right?
What do you mean by copy?
That is, the numbers in the front 3 by 3 are the same as the numbers in the weights in the front 3 by 3 are the same as the weights in the middle 3 by 3.
I don't think same is the right word, because the weights will be different.
Well, then what's the difference between the orange, red, green model below and
the difference is to get 1 pixel out on the top, you have to do 27 operations, right? 3 by 3 by 3.
Yes.
Whereas if you go down, you're trying to break that into 2 different parts. So the 3 by 3 is first going to just give you
9.
Yeah, but that 3 by 3 can only be run up and down that 7 by 7 by 3 linearly. You can't. It doesn't have a third dimension.
Right. It won't be run across the top.
Yeah. So it's being applied to the individual channels in the same way as the. I don't see the difference. In other words, my doubt is I don't see the difference between the orange block on the top and the split block on the bottom.
The top one is not applied on each channel, right? It's applied on the combination of channels. So you drop that cube in there, the 3 by 3 cube into that 7 by 7 by 3 cuboid, and then all your 27 pixels get multiplied into all the 27 weight filter pixels, position by position.
Okay, and then you end up with a single 5 by 5.
Exactly.
I see.
No.
Got it.
That will yield just a single pixel. When you run that throughout this whole cuboid,
yeah. So if you apply the convolution to the entire left-hand blue cube, you get 1 slice of the green cube on the right.
Exactly.
Yeah.
Okay.
128 of those is what gives you the depth, which is the filter dimension.
Thank you. I see that now. Yeah. Great.
Okay, so that's why this is fascinating, because with the pictures it becomes much easier to understand, or else you kind of like muddle along. And
I think also that's why they have this 1 by 1 convolution at the end of the separable depth-wise convolution. They normally pass those 3 channel at the last figure. Those 3 channel concatenated. No,
I think the figure below will be more clear.
Figure below, yeah. When they do when they use this, when they do this, that's it. They with the 5 by 5 by 3 figure when they concatenated the results, they go they pass it through a 1x1 convolution to set the number of channels.
Yeah.
They can go like a 1x1 by 128 features, and then and then
apply multiple 1x1 to modify depth.
They end up with the same. They end up with the same green block, or at least a green block with the same dimension, but it's derived differently because it has linear combinations of all of the 1x1 convolution is basically is adding up a linear combination of those 3 filters.
Yes. And secondly, that's a good
that's why they replace the normal convolution with the depth-wise convolution. They have the same ending result, but they have much fewer parameters.
Not same ending result.
In fact, that's the key, that the efficiency here, they do this multiplication, and that one is what makes it very clear. So if you can read this particular stuff, or I should say that's where you get the advantage.
Right. Yeah, that's what. So I think if you go back, like you pointed out, Srinivas, there is separable convolution. Separable convolution will yield the same result either way, if you don't do it separable or if you do it the separable way. But depth-wise separable is not going to yield the same result. It's going to yield a different result.
Of the same dimension.
Yes, same dimension, yes, because that's architecture dependent, right?
Yeah.
And
also less multiplication, right?
Yes,
as shown
exactly.
Here.
Yeah. So that is the kind of the trade-off you're doing with your convolutions, right?
Correct.
It's not going to give you the exact mapping.
It's not giving you the same,
right?
But it still gives you
close enough.
Eventually, eventually the results are better.
Right. And the other point is that I think going back to what you initially kind of mentioned, referencing CS224, and there is still a depth-wise combination happening here too, which happens in the other normal convolution also. So you're not kind of violating the convolution aspect of mixing channels on the depth. You're just doing it at a different stage here.
Yeah, because you're doing the 1x1 to
right.
bring that into play. Yeah, exactly. But by doing this depth-wise separable, you're reducing, the reason the efficiency goes up is because of this comparison of multiplications that we talked about. That's why it's cheaper computationally to do a depth-wise.
Mm-hmm.
And in addition to this efficiency, you're applying the efficiency of 8 rows, which basically gives you the different depth of field or receptive fields by, parallelizing and just changing the rate. Right? Because otherwise, previously the alternative is to do this, you'll see in the paper, they drop the grid size variation. They don't have the grid size or variation.
Even if you consider without the truce for a moment, just for simplicity, and then if you compare the original process to the depth-wise separable convolution process, it seems like you're getting something for nothing, because not only do you get a improved, fewer calculations, but it seems somehow that it's capturing more. It can capture more, because in the first case you're just taking the average of those 27 pixels, but in this case you're actually taking linear combinations of 3 groups of 9 of those to get the 5x5. It seems like it can capture more of the features. It captures more of the differences between the channels in some way. I don't know.
No, it's an interesting observation, but what I have not seen is exception in case of ImageNet and other things giving and comparison of just the classification results. I've seen it. Have you seen anything of that kind, Rakhil, or in Mehul or Steve?
I think that the traditional convolution makes more sense to me when it comes to like images, is because in a channel there is dependency, like there is spatial dependency. Whereas when you try to do it depth-wise, it's kind of slightly different, but the math somehow seems to work out.
It gives you a way of weighting one channel over the other in some way. But I guess the 27 pixels can fold that in automatically, even if you don't separate them depth-wise. Okay, so forget what I said.
No,
Yeah,
that's an
it's kind
interesting
of an
observation
interesting
because they don't point out that anywhere, like why one is better than the other, other than the efficiency part of it.
Yeah, they do
yeah.
not.
I was sorry. Sorry. I just stepped away for a minute. Yeah, I think so. Before, not from deep learning, but just from before signal processing and image processing, it's just the separable part is just efficiency, right? Like you have a 2 by we we had a
Yeah.
3 by, yeah, and I didn't follow if there is like any other benefit other than but the efficiency benefit is huge, right?
Yeah.
But
Yeah.
the separable thing is different though. The separable thing will yield the same output.
Okay, here there is
Here it
another,
doesn't yield the same
the thing he was
Oh,
referring to is this separable convolution is different from depth-wise separable convolution.
Oh, I see.
Sort
And
of
what
derived from it, but it's not the same output you won't get. There, it's just doing math in 2 ways to get the same output. Here, you're doing math in 2 ways to get somewhat the close output. It's not the exact same output.
Okay, sorry, I missed that.
And you can see this highlighted thing, right? That although spatially they save cost, it's rarely used in deep learning. One of the main reasons is that not all kernels can be divided into two smaller. If we replace all traditional by the spatially separable, we limit ourselves for searching all possible kernels during training, and the retraining result may be suboptimal.
Yeah, that's what I was going to ask next. I was just going to ask whether all kernels can be separated, and I don't think they can, but he answered that right there. Yeah.
Yeah. So I think that's why this thing it's a real good reference to go through and understand all these different convolutions. Because I was getting lost in the glossary of terminology and stuff. And by the way, to confuse, as I said, there's even depth-wise separable, and the paper he refers to throws in yet another stuff. But I think if we can go through this paper, that's good. Okay, so can I switch back to the original paper now that we have looked what depth-wise convolution is? And let me post this and share this screen to go back to 1 second. I need to get my okay, let's see whether I get the right screen. Are you guys seeing the paper again, or am I lost?
Yep.
Okay, good. Okay, so let's keep moving. Depth-wise separable, and then encoder decoder with ATROS convolution. This is where they talk about ATROS depth-wise. So this is fairly easy to understand. It's just a combination of depth-wise separable convolution and ATROS convolution. Because the two are orthogonal in a sense, they can be combined. So you just apply ATROS convolution, but you do it depth-wise separable. So you do it per channel. And that's what they are doing when in this paper. So,
So is it true that every ATROS convolution can be represented as a depth-wise separable convolution?
There is nothing there with ATROS because there is no math involved, right? It's just including that rate. It's just changing the rate of sampling. And so sampling every pixel, you're just sampling at a rate of pixels. That's all the difference is.
Yeah, it's only the difference between this picture and that picture. And the only difference is you see that it's sampling not every other or the next pixel 3 by 3, but missing every pixel in the X and Y dimension.
Right, but is a convolution like that, is an ATROS convolution always separable? That's the question.
That's what the separable part is not. You're not doing mathematics separation here, right? The separation here is you're applying it channel by channel and then doing the 1 by 1. You're not talking of the separable part, which we spoke previously.
Okay, because I was confused. I thought that somebody said that every reference to an ATROS convolution is really referring to a separable ATROS convolution.
To an ATROS depth-wise separable convolution. So the resulting convolution, so bottom line, they are calling what they are doing in C as ATROS separable convolution.
That's very confusing, especially because separable convolution has been defined to be a convolution that can be separated into two factors.
Separable convolution is not involved in deep learning, so we can kind of remove that out. That is just signal processing, nice math, given a filter, you can split it.
Right. But I think that, you know, a separable convolution means a 2x2 matrix that's expressed as the product of a column of a, you know, 1 by 2. Well, a k by k convolution filter, if it's separable, is expressible as a product at the outer product of a
1 by k and k by 1.
Of a 1 by k and k by, oh, well, actually, yeah, 1 by k and k by 1, that's right. And so when they say separable convolution, that's what comes to mind. Now they're introducing a different definition of separable convolution. And
they're basically saying the depthwise convolution covered in the exception paper or the exception paper, which does the depthwise convolution followed by a 1 by 1, which we just saw as an example. They apply the Atros convolution in that manner, and they refer to that. When I say in that manner, what I mean is they, instead of taking this 27 3x3 3 layers or 3 channels, they apply it channel by channel, and they refer to that as Atros separable convolution. They are defining that as Atros separable convolution.
So what's the difference between an Atros separable convolution and an Atros convolution?
And an Atros convolution would apply this spreading out of every other x and y, but would still have 27, I mean, it would not apply it channel by channel. It would apply it across all 3 channels. Like it's the same thing as we saw in the depthwise.
Got it, okay.
Right, so that's the enhancement they do. So as I say here, Atros convolution combined with the concept of depthwise separable convolution, and that's what they call as Atros separable convolution.
Okay, depthwise. It seems like a better word would just be called, it would be better if they just called it a depthwise Atros convolution or something like that.
But
anyway,
that's
because they're mixing up the sense of the word separable in 2 different things, and that's confusing. But anyway, go ahead. I'm sorry.
And then we already know that output stride is the ratio of the input image, ratio of input image to the resolution, spatial resolution of the final output. So it's the H by W ratio of input image to the final output before the global pooling or fully connected. So as they discussed, it's typically 32, but sometimes it's 16 or 18, and we'll get to what they eventually do. And then we use the last feature map before logits in the original DeepLab v3 as the encoder output in our proposed decoder structure. So that is this guy that they combine, that they begin to combine into the decoder structure. And then let's see. So the proposed decoder. So the encoder features are first bilinearly upsampled by a factor of 4, then concatenated with a corresponding lower level feature. So this is just explanation of the diagram that we have seen up above here. They just in words explaining this diagram that we saw by using this language here, and then apply another 1 by 1 on the low level to reduce the number of channels. This is, as I said, to align the number of channels coming into you from the encoder and directly from your input path. And then after the concatenation, you apply a few 3x3 convolution to refine the features, followed by another bilinear upsampling by a factor of 4. So if you see what they are describing is this is not just a single 3x3, but a few 3x3s. And then they get it down to where it's, when it is upsampled by 4, it gives you the prediction. So that's the description of what's going on in the picture up above. And then this exception network is what introduces, or that paper is what introduces the exception model 26 is what introduces the depth-wise separable convolution. And then there's another paper where this 31 where exception is used as the backbone, and that's what these two things refer to. You can go look at 26 and 31, but how the combination occurs is what is shown in these, in this fairly detailed flow. And here, this would have to be kind of compared side by side with the code. You take the images, you do the 3x3 stride 2, convolve 64 3x3, and kind of feed forward sometimes. So you go through, and then these are regular convolves at the beginning, and then you begin to do the depth-wise separable convolutions. And so this is your entry. This is, you can see how many times they do just 3 levels of separable convolution, repeat 16 times. And again, the exit flow, and each of these details, I think we would need to look at the code and align it with this in order to get the complete, understanding. But the key thing they also seem to benefit from, which they do not call out in the DeepLab v3 paper, is they do extra batch norm and ReLU after each 3x3 separable depth-wise convolution. So what this means is each of these, every single one of these purple things is followed by a batch norm and a ReLU, a batch norm and a ReLU, a batch norm and a ReLU. And then when you repeat this 16 times, there's a batch norm ReLU after each of these guys. So that's a lot of computation to go through, and you can see this, how deep the stack is as well. Right, and then the rest of the paper is the evaluation of the results. And one of the things they talk about is you could think of the direct 16x upsampling that happens in the DeepLab v3 paper as just another simplistic decoder. And instead they are using a more complex decoder in this case. And they play around with different aspects of the decoder and how many filters to use, and should they use a single 3x3 or multiple 3x3s, and so on and so forth. And eventually they come down to one conclusion, that is the output stride is 4. And here I had a question, maybe Raquel, if you've gone through, you can answer is, so sticking with an output stride of 4 tells me then that you're not going any deeper, because an output stride of 4 means that your input image means that on the encoder part, you have not very significantly reduced your input. Or does it mean that you just do the comparison when your size is 1/4 of your input image? Which of the two?
I think it goes deeper, right? In this case, if you go back to the DeepLab v3 paper, because output stride is defined by spatial resolution of input divided by like the spatial resolution of the output.
Correct. So, but 4x would
down
mean
the cascade.
Yeah. So if you see here,
I think is this the v3 or the v3?
This is the v3 paper. Yeah.
Ah, okay. Then if you scroll down to the cascade figure, you should see output stride. There you go.
Right, but output stride of 4 would mean that it's not as small.
Oh, yeah, correct. Yeah, you're right. Yeah.
Right?
Yep.
That's what I understood. So that means if you're saying in this paper that you're sticking to output stride of 4, that means so my question is it just that when they evaluate the results, they are doing it? Or is it that the depth of the encoder itself only takes you to 1/4 of the size?
I haven't looked at the V3 plus code, but yeah, that's what it sounds like. We do not
Yeah,
proceed
so we'll
further
need to
than
look at
third
the
out.
code
Oh yeah,
when
but yes,
it,
a feature map that is output stride is less than 4. So you're right. It stops at 4.
yeah.
So
So
the
which I thought was interesting because it's not an 8 or a 16. So it doesn't go as deep if I understand, but we have to look at the code to that more was my
So that's kind of the trade-off, right? If it's sticking at 4 rather than going down to 8, 16, or 32, that means you would have had a lot more computations because your feature map is that much more bigger. But then the trade-off here is you're not doing regular convolutions, you're doing depth-wise convolutions.
Correct.
And if you remember in Deep Lab V3, the paper again says, we tried output stride 16, we got X number of accuracy, but trying output stride is equal to 8, which means a bigger feature map, we got higher accuracy.
Yes.
So they're doing it at a higher resolution, but not taking the hit of computation because of the depth-wise convolution.
Yes. But what I was concerned about was it seemed like not going further deep in the encoder side is not hurting them in terms of performance on the segmentation task, which is interesting because, like a unit and stuff, you go all the way to a much smaller h by w before you come back up. And it seems like that depth is not necessary if segmentation is your goal.
Yeah, this is the part which I don't know how you kind of evaluate. In the unit, you kind of know, right? You start from the original, you go down the chain, the encoder, and then you come back up. With Deep Lab V3 and V3 Plus itself, you can see they say output stride 4, 8, 16, 32. So how do you choose which one? I don't know.
Exactly. And by the way, they don't prescribe anything. They just say we get better results and they stick with it. Right? And they do an amazing thing, which I'll come to in a minute. Hopefully we can finish up. So then in the interest of time, you can go through it, but they use ResNet 101 as the backbone and exception as the backbone. And as we saw earlier, bottom line, what it means is exception does the depth-wise separable piece, and ResNet obviously includes normal convolutions. And they show that, you get better results and you with the exceptions. The other thing is with the decoder, with MS, and MS I think would be multiple strides, this multiple
scale, I think, right?
Multiple scale, sorry, scale. So this multiple scale refers to the size of the images. So you do all these heteros and other stuff at multiple scales, and then you flip horizontally left, right. And what they show is when the eval OS, and OS stands for output stride. So, and this is the interesting part, right? The train OS they do at 32, which means while they're training, they're taking the encoder depth down to 32. But then when they evaluate only at 8, right? And you can see what to me was interesting, even though the MIOU of the guy with decoder, multiple scale, and flip is at 80.57, which I think is the highest here. Look at the number of multiply adds that it does. And then you look at just adding the decoder, 32.8, don't do the multiple scale, don't do the flip, and you get at 297, which is like, what's it, even if you round to 200, it's 5, and then another 5. So 25x less, and you're at 77.9 versus 80.57, which, it's not the point they want to make, but I just thought was interesting.
I have a question there, actually, since you bring that up. Why is the multiply adds increasing? I mean, is the MS and flip playing a role, or is it just because your train OS and eval OS are like that? Because I don't imagine they would calculate multiply adds for each and every flip, right? Which basically means twice the number of multiply adds.
The flipping is augmentation, so I would,
correct.
no.
Same
so
with multi-scale also.
Multi-scale would, right? Because multi-scale, you're generating data at...
Just your input image is changing scale, right?
Yes.
You're either doing 1x your size or you're doing 0.5x or 0.2x.
No, I thought multi-scale meant that you're doing multiple of those and then combining them. Remember that in DeepLab V3, they kind of had this thing where they changed the scale. It's another thing that they vary.
So you're saying they change the scale and train again? So you train one at 1x and then you retrain that model with 0.5x?
Or yes, that's my understanding, but I would need to go back and check. But that's the only way you can explain the thing changing with, see, if you compare even between these two, the encoder, decoder, or the encoder train and eval OS remains the same, 1616. But
yeah, you're right. Okay,
you can
I
see
that.
the multiply adds changing by almost 9x.
Yeah, that's interesting. Yeah, let's look at that. Okay.
Right. So interest of time. So we just prefer using output stride as 16 or 8 during training or evaluation depending on the complexity budget. I mean, we kind of discussed that the fact that it has a direct impact on the complexity budget. So, and then what is fascinating to me is the decoder actually provides very small benefit, at least when it comes to final results. But then when they evaluate it based on, you know, the output edges of objects, then they get a much better result. So you can look at it that, you know, those results are all provided in where I've said the, so adding decoder, see, brings about 0.8% improvement, is less than 1% improvement for all the different inference strategies. So you go, really? I mean, you've done all this to gain 1% and publish that as a paper, but the interesting thing is, you know, eventually when they combine other things, then it becomes more important. So, and that's why they say the proposed decoder module near the object boundaries. So it provides significant benefit, not just in the final result, but in the fact that it helps you near the object boundaries where you suffer from problems. So that's what I meant by this comment, that the overall performance hides the specific benefit of decoder use. If you guys think otherwise, please chime in once you read the details. The most, and then they say all this, and then this thing really blew me away. It kind of shows where deep learning is in general. They went through all this trouble, did this image pooling, and then look at what they say in this paragraph. I was just blown away by this. They say, we noticed that removing the augmented image level feature improves the performance, showing that in deep lab model, the image level features are more effective on the Pascal VOC 2012 dataset. So they just dropped the image pooling, which they added as something in V3 and V3 plus, and just said, well, it just helps in one of the data, so forget it. And they don't even explain why, which kind of blew me away. So it, you know, that just goes to show you that it's still fairly empirical in the sense that, you know, if one set of data you use image level pooling, it gives you better results. With the same architecture and stuff, you have a different data set and you don't see the same results. So you just drop, and you see better results when you drop something that you're doing. Okay, any comments?
This is very intriguing, but I think it's because image level that they have much more representation on the feature level than on the image level. The information on the feature level is much more representative for the network than the image level information. It's kind of more it does more damage than improvement on the.
Yeah, but you know,
but it's a very interesting observation.
Yeah,
and I understand why Srinivas is upset, because it upsets me too. I mean, if you're doing this scientifically, and then you just say, oh, well, we're just going to arbitrarily drop this for this data set because we get better results, that's not fair. I mean, you have to, if you're writing the paper, you have to explain why you got better results when you didn't use your fancy technique.
Yeah, and also, like I say, I mean, your argument to this point, and I bought the argument, which is why I'm like, okay, I shouldn't buy the argument as quickly, is the image level context, when provided at lower resolutions, helps you better segment. I mean, that's the whole reason why you bring in higher level context, blah, blah, blah.
Yeah.
But then when you apply it to a different data set and then you say, oh, image pooling, if I drop it, it actually gives me better results, then at least do me a favor and say, why in this instance is your intuition and explanation that held for all the other things doesn't work here?
Yeah, and you know, it's kind of like reminiscent of p hacking, right? Where you try different things in order to get the best p value, and you just kind of cheat. I mean, you know, it's like it doesn't give me confidence that this method applies generally.
Yeah, yeah, and you know, you're Google. I mean, you have all the computing in the world. If you aren't going to explain it, I mean, nobody else in the world is going to.
Yeah.
So I was like, you know, at the end of the paper, I was like, really? You just blew away a significant argument that I thought, you know, that I totally believed in.
Yeah, it's like the cow kicking over the pail of milk after you milk her. Right?
So the complete global context stuff is not gone, right? Image pooling is just removing one aspect of it.
Yes, yes, I understand.
The
I mean,
dilation rates are still there, so you still have the global context. I agree with what you're saying, but I again feel like even like implementing these different pieces of code, when I run everything, surprisingly dynamic unit gives me the highest accuracy, and I'm like, why did we move from that? So I agree with that, but then.
Yeah, no, you're right. My reaction is a little overwrought, but you know, so yes, they do a lot of the other stuff, which still says that, you know, a lot of it is still relevant. But my comment was more exactly what Joseph is saying. Explain it to me. Like, why do you see that discrepancy? It's a discrepancy, right? And it's a significant one.
Yeah.
Right. Or call it out and say, look, we found this weird result. We weren't able to explain it. Maybe you can, or something like that. You know?
Yeah, or further work.
Yeah.
Like this calls for future work.
The data set with the cars, and is that the one, the street image one?
The image features are more. This is the cityscapes.
Cityscapes, yeah.
But no, wait. I thought the one we were talking about now was Pascal VOC, or
no? They say that we noticed that removing improves the performance, showing that image level features are more effective on Pascal, which means they are less effective on this, and this is cityscapes.
Interesting. Is that the reason? I mean, I'm just eyeballing here. Didn't we kind of figure out that cityscapes were much huge images compared to the Pascal VOC images?
Yes.
So if you try to compare both at, let's say, output stride 4, one is going to still have a huge map, which is going to still have a lot of fine detail, whereas the other one is not going to have that much fine detail, right?
Yes.
So,
but if that was the reason, I would appreciate them saying that. Because that's a simple one-liner, right?
Right. But I don't know, how do you verify if that is the reason?
Now they have the compute, so they go and do kind of.
I don't know, like, because the problem is one is at a smaller size, so you have to bump that up, and once you start upscaling, then you're not adding information technically, right? You're just
I mean,
I don't know how they would.
I agree that it requires further thought of how to tease out that particular. But
maybe this aspect might be the most explainable, the difference in the data set aspect, because I read recently a paper when they compare a UNet-based segmentation procedure model with the Deep Lab V3 model on 2 data sets, and one was big data sets of forests, aerial images from forests to segment the top of all the trees, and the other one was like more fine grain crops, and then they had better results using ImageNet than with the Deep Lab on the bigger data set with bigger images, because it was UAV images from the top of the forests. So the segmentation was a very it was a huge image, like 5,000 pixels by 2,000 pixels, and I believe that Deep Lab V3 is more it's more effective on on segmenting smaller stuff, smaller objects.
Maybe that's because it was trained on the smaller images, and maybe if somebody wanted to, they could construct a special set of filters for larger images that would work better. Maybe that's the problem, is that it was optimized for the smaller images.
Yeah.
Yeah, but I just thought, you know, that was something I found. It's towards the very end, and they just kind of threw it in there, and I was like, wait, don't just try to slide it past me. But anyway, so I think, sorry, Steve, we took up the entire hour and a half going through this. So next time we'll start with you, and Mehul, if you could maybe see whether you can be ready by next week, then we can have you discuss TPU usage, and Steve can start us off with kind of Catalyst usage as well.
I guess soon we should have FastAI to support for TPU too, so that'll be fun.
Sorry, as FastAI got TPU support now?
Not yet. It should be, because Jeremy had posted that that is something he'll be looking into next. So,
right.
So that'll be like good to have everything on that, even if we can have Catalyst and this.
Yeah, so I think that would expand our set of capabilities, I think, because Catalyst is a platform which Steve has used, and if he can share that of what and how, and that'd be great. And Mehul can at least get our toes wet, even if it's TensorFlow, Kaggle.
We can actually start working on these different things and in reality ensemble our final results and then submit. Yeah. And we don't have to worry about compute, because we'll be kind of working on separate things at that point of time. We don't have to try all these different combinations that currently I think only Mehul and you, Steve and you are trying out with minimal compute hours.
Yeah. So. Yep. And Steve, Bannister Steve has managed to beat, and I haven't yet caught up because I've been like not submitting the last week or two. So. Okay, thanks everyone for joining. Next week we'll start with Steve and Mehul, and if we have time, then we'll go over Rakel, the PSP.NET implementation as well.
Yeah, so I think PSP.NET, DeepLab v3. I had one more, my own implementation of combining ideas that we learned from UNet and DeepLab v3 that we can share. Again, I got slightly low results, so we can kind of see why it is low and how we can change things. So
yeah, that'd be great. And then HRNet, I annotated and posted as well. And that's a much better written paper, although I have to admit, I drew a blank right when it came to the details, right in the middle of the paper. But then the results and the leading up to what they're trying to do, I got a good idea of. So
I agree. I also think that's a much simpler paper. But the code was a lot more harder for me to understand.
Yeah, no, even the meat of it is much harder for me to figure out on my own. So we'll discuss that maybe 2 weeks from now.
Sounds good.